Hello everyone. Let's take some geometrical examples on equivalence relations today. So the first example that we're going to take is, let's say we have a relation, let L be the set of all lines in a plane and relation R be defined in L as L1, L2 if L1 is perpendicular to L2. So we have to check the equivalence of this relation. Now remember, to check equivalence, we majorly check three properties, which are, one is reflexive, second is the relation should be symmetric, and third is the relation should be transitive. So let's one by one check all these properties for this relation, starting with reflexive. So for reflexive, let's take our plane in which we'll construct the lines. So this is our plane, and we have to show that L1, L1 would belong to the relation, right? The line with itself is related on this relation. So let's take any line here. This is the line. Let's call it L1. And let's see if it's perpendicular to itself or not. So let's take this line. So we have this line. And this line with itself, let's take L1 again. So this is the line itself. Clearly, it won't be perpendicular to itself. Rather, this line would be parallel to itself, right? Since it's not perpendicular to itself, it's clear that they can't be part of the relation, right? A line should be related to itself for it to be reflexive. But we can see the line is not related on this relation. Thus, it's not perpendicular and L1, L1 does not belong to the relation. Thus, this relation is not reflexive. So let's mark it. It's not reflexive. Let's check symmetric now. So for symmetric, what we have to show is that if there's two lines L1, L2 which belong to the relation, which means that L1 is perpendicular to L2, I have to show that it also implies that L2, L1 also belongs to the relation. So let's take our plane again and let's take two lines. So first we take our L1 and let's take a line that is perpendicular to L1. So somewhere like this we have another line L2, and you can see here is the 90-degree angle, and thus these two lines are perpendicular to each other. Since they are perpendicular to each other, we can say that they belong to the relation R. Now let's take the line L2 and let's try going backwards. Knowing that L2 exists, we can also say that L2, L1 belongs to relation R. So let's make a line perpendicular to L2. So a line perpendicular to L2 would be, this is the angle 90 degrees. So a line would somewhere go like this. So a line would be like this. And if you look at this line and you look at L1, you will realize they're just the same lines. So it's L2, L1 also being perpendicular. And thus L2, L1 also belongs to the relation R. So from this fact, we got this fact, and this clearly means that this relation is definitely symmetric. So we have symmetric, yes, this relation is symmetric. Let's check the last property, which is transitive. So for transitive, what we have to show that if there are two lines L1, L2 which are perpendicular to each other, and that's why they belong in the relation, and there's another two lines L2, L3 which are also perpendicular and they belong to the relation, we have to show that L1, L3 should also belong to the relation. So let's take our three lines. Let's take our plane. We have a first line L1. Let's take the perpendicular line L2 because we know that L1, L2 belongs to the relation. This is not we're proving. This is what we already know. So this is L2. And let's take a third line L3, which is also perpendicular to L2. Again, a fact that we already know. Based on these facts, we are trying to prove this. So this is L3. It is clear that this is the 90 degrees here and this is the 90 degrees here, and that's why they are perpendicular. 90 degrees here, whereas this is 90 degrees here. These are perpendicular lines, and thus L1, L2 belong to relation R and L2, L3 belong to the relation R. Now let's check out L1 and L3 individually. So we'll see L1 is here and L3 is here. And clearly these lines are not perpendicular to each other, but again, they're parallel to each other, right? And that makes sense because if L2 is perpendicular to L1 and L2 is perpendicular to L3, it must happen that L1 and L3 should be parallel if they're lying in the same plane, right? So they are not perpendicular, and thus L1, L3 does not belong to the relation R. So this relation is not transitive. So this relation is not transitive, and for equivalence it has to be all three properties, whereas this relation is only symmetric. Alright, so this is not an equivalence relation. Let's take another example. So we have another relation that is defined as the set A of all polygons, in which P1 and P2 should have the same number of sides. And we have to show that this is an equivalence relation. So again, for an equivalence relation, we have to prove its reflexivity, it's symmetric, and also that it's transitive. So let's talk about reflexive first. So for reflexive, let's take the polygons. I'm a fan of football. So the polygon that I'm going to consider is the pentagon, is the five-sided pentagon that is there on footballs. So let's take our football. You can see the pentagon here. And let's try seeing the number of sides here on this figure, right? That's the shape of the figure, and the number of sides would be 1, 2, 3, 4, and 5. So it's clear that this is a pentagon, right? Now for reflexivity, I have to compare this with itself, that it has the same number of sides with itself. That's why it would be related to itself. So let's take another football with another figure here, and let's understand the sides here, number of sides here. So it would be 1, 2, 3, 4, and again 5. So this football also has 5 number of sides in this pentagon, right? It has 5 sides, that's why I'm calling it pentagon. So this also has 5 sides. So it clearly means that these two figures have the same number of sides, and because they have the same number of sides, a football, at least the figure on this football, would be related to itself. This polygon would be related to itself. And it's clear that every polygon will have the same number of sides as itself. That's why this relation, we can safely say that it's reflexive. So it is a reflexive relation. So first property is tick marked. This is a reflexive. Let's talk about symmetric. So suppose we take the example of our football again. And this football has 5 sides, as we just saw. And another example that we can think of is a back of a wooden house, right? It's something like this, and we can get the shapes here. We can get the sides here. So that's 1, 2. That would be 3 and 4 here, and there's a fifth side here. So we can see that both of them have the same number of sides. So that's why they are related, because they have the same number of sides. So we can say the football pentagon and the house pentagon are related. They belong to the relation R. Now for symmetric, we have to see that if we take this house example first, if we take the back of the house first and we count the number of sides, which is 1, 2, 3, 4, 5, that's 5 sides. And now we count the number of sides of the football, the figure in between, and that's 1, 2, 3, 4, 5. It still happens that this has 5 sides and this has 5 sides. So still the number of sides of this would be equal to the number of sides of this. So when we were taking the football first and we were trying to check its relation with the back of the house, we say that the football pentagon and the house pentagon are related. But now that we've taken the house pentagon first, the back of the house first, and now we're checking whether they are related, which eventually comes out that they are related, then we will write it as house pentagon, comma football pentagon belongs to the relation R. And because this follows straight from this, so we can say that it is symmetric. And simply because if two polygons P1, P2 belong to the relation R implies that P2, P1 also belongs to the relation R, then we can simply write that this is definitely a symmetric relation too. So it is also symmetric. And let's talk about the last property, transitive. So for transitive, let's take the example of a football having our 5 sides. Let's take the example of our back of the house, which it is related to, which also has 5 sides. So when this happens, we can write that football pentagon comma house painting, which are two polygons, they are related. They are there in the relation. Now let's take another example, taking this back of the house, and let's take the example of a shovel, right? We know that this has 5 sides, and let's take a shovel here, and let's see what the head of shovel, what figure it is, right? It's amazing how we can find math in the most basic things. So let's check the number of sides in the head of a shovel, and we see that it also has 5 sides. So this means this back of the house is also related to the shovel. And we can write the house painting is related to the shovel painting. So they belong in the relation R. So if this and this belongs to the relation R, whereas this and this belongs to the relation R, what we have to show that the football painting and the shovel painting should also belong to the relation R. So let's keep all of them side by side and our shovel painting. And let's take out our house painting now from the between. And we can see that the football painting has 5 sides. This shovel has 5 sides. So it clearly means that both of them are also related to each other. And thus, we can say the football pentagon and the shovel pentagon are also related and they belong to the relation R. And this fact is strictly implied from both these facts that we already knew of. So when this happens, this means the relation is also transitive. So this was a reflexive symmetric relation already. Now we also proved that it's a transitive relation. That means since it has checkmarked all the properties of an equivalence relation, this relation can be said to be an equivalence relation. So that's all for today. Thank you.